Alright, hello again. We're going to tackle chapter 13.1, which is Introduction to Factoring. The first thing we're going to do here is learn about the greatest common factor, which I will shorthand as the GCF throughout. Now, there's three words here. The most important word is factor, and it's very important we know what that means. If we were to have a number like 2, and we were to write out factors of 2, we would have to think of two numbers that multiply together to get us 2, or more. There's actually only two numbers that work, 1 times 2. So 1 is a factor of 2, and 2 is a factor of 2. And if we could find more, we'd list them off. Now, we want to find the greatest common factor between two objects, two numbers. So let's go ahead and start with our first example, in which we're asked to find the GCF of 12 and 16. So we can do this a couple ways. We're going to start off with the most basic form. We'll list all factors of 12. Like 1 times 12 is the easiest one. And then we could say there's 2 times 6, which is also 12. And then we could say there's 3 times 4. And these are all factors of 12. And then we can list off all the factors of 16, in which we have 1 and 16, 2 and 8, and then last but not least we have 4 times 4, so we just have 4 ones. And you know you found all the factors once you start repeating yourself, like 4 times 4 and then we're done, we can't go any further. We got 3 times 4 and then 4 times 3. So some people call this a factor rainbow, where they connect the 1 to the 12 and 2 to the 6 and 3 to the 4. Now, we are interested in the greatest common factor, so what they share. Well, they always will have 1. No matter what you do, you will always have a GCF of 1. No, I'm sorry, let me say that again. No matter what you do, you always have a common factor of 1. It might not be the greatest, though. There's also 2 here, in which they both share, and 4. Now, we're interested in the biggest one, the greatest common factor. So the GCF for these two numbers is 4. They do have common factors of 2 and 1, but we want the greatest one. So that's how we find the GCF. This is nice. If the numbers are very small, we can list them off, and we could even kind of picture it in our head sometimes if we're really good with our multiplication tables. When the numbers get a little bit bigger, we have another method that we do. So let's say we want to find the GCF of 27, 144, and 63. This one's a little bit more difficult. So it might not be easy for us to list off all factors of 144. It would be a little bit of a pain. So we are going to use the prime factorization, and then we're just going to collect all the primes they share in common, because the prime factorization will break these down into the building blocks of prime numbers, and prime numbers build off all our factors, so it will be very nice to us. We'll start with 27, in which we make the tree when we want to find the prime factorization, and we think of two numbers that multiply together to get us 27, so we got 3 and 9. Since 3 is prime, we can stop, 9 is not, so we keep on going, and we form our tree. And we'll do the same thing for 144, so we could have 12 and 12, maybe 2 and 6, 2's prime, 6 breaks down into 2 and 3. Excuse me. For 144, we're looking at the 12, so it could break down maybe 3 and 4. I felt of interest, so we'll do 3's prime, 4 breaks into 2 and 2. It doesn't matter what numbers we pick because we're always breaking down into the prime numbers, so there's no errors here unless we don't know how to multiply. So 63, we have, let's see, we could do 3 and 21. 3's prime. 21 breaks into 3 and 7. You could have done 9 and 7 if you saw that, whatever you see fit. Okay. And now let's go ahead. I'm going to draw a line between these because they kind of are getting close to one another. And we're going to collect the primes they all share. So we only want things they have in common. So let's see. This guy's got a 3. So for sure 27 has a 3. If 144 has a 3, we're doing good. Yep, there's a 3 there or there. Doesn't matter which one you pick. And 63 has a 3. So since all of them share a 3 in common, that is part of our GCF. But wait, if there's more that they share in common, we collect it and we'll multiply them together. Let's see if there's more. There's a 3 here. Oh, there's another 3 and another 3. They all have to have it though, not just 2 or just one of them. They all must have the 3 in order for us to take it. So there we go, we have 2 3s. Let's see if there's more. We have a 3 here. All the 3s have been used up here, so there's no more, so we can't collect any more. And there's no other 3s here because we've used them up already. So that's it. And there's no more numbers to the 27, so there's no way it will share anything else. Like if we said 2, well, 27 doesn't have 2. Neither does 63. And you might be, well, what about the 7? Well, 144 doesn't have 7, and neither does 27. So no 7's there. So all we have is 3 times 3, which gets us 9. So 9 is the greatest common factor of 27, 144, and 63. Okay. Let's go ahead and get a little bit more complicated. Let's find the GCF of monomials. So let's say our first one will be nice to ourselves. We have x squared, x to the 4th, and x cubed. So here's our 3 things that we want to find the GCF between. I don't have any constants because I wanted to be nice. So we're looking at variables. You can do the same thing we did before where we form a tree, so to speak, in which x squared really means we have x times x. X to the 4th really means we have x times x times x times x. And let's get tedious, we have x cubed, which is x times x times x. So there we go. Now, I don't know what x is, so we might be finding a prime, we might not be. I'm just going to call it prime, so to speak, and say these guys are my primes. And I'm going to collect what they all share in common. So only what everyone has. Well, there's an x here, there's an x here, and maybe I like this x, so there's an x there. So if I take all 3 of these, they all share an x in common, so my GCF is going to have an x. Now there's another x, and another x, and another x. So all 3 of these gives us another x. But now we've run out of x's, so there's no way we could collect any more. So all we have is x times x, which gets us x squared. Pretty much what we are going to think about for variables is the smallest degree will win. And let me say that again a little bit differently. So look at our degrees. We have x squared, x to the 4th, and x cubed. This says we have 2 x's multiplied together. This has 4 x's multiplied together. And this has 3 x's multiplied together. The most that we will ever share in common is what the smallest degree is, which was 2 of them. We can't have any more because this guy doesn't have any more to give, so we can't collect any more. So for variables, the GCF is always the smallest degree of that variable. Now you might be thinking, what if we have more than one variable? Glad you asked. So let's go ahead and tackle another one. Let's say we have xy squared, x squared y, and I don't know, let's be crazy, x cubed, y cubed. So we're looking at the degrees. They're going to help us out. We have x for one variable, and we only look at the same bases, because we're going to treat this, well, there's only one x, and then there's 2 y's. We treat them as 2 different types of primes. Same deal here. We have x squared, so we have 2 x's, and we have 1 y. And then worse here, we have 3 x's and 3 y's. And now we just need to collect what they all share in common, which pretty much will be the smallest degree for us. So there's 1x, 1x, and 1x. And this guy doesn't have any more x's, so that's it. So we got 1x. Now move on. We got a y, 1 y, and that's all he has of y's, and a y. So all we can collect is 1 y. We can't get any more. So really the smallest degree of each variable, so x's smallest degree was to the first, and the smallest degree of the y's was to the first, gives us our GCF. Okay, so not too bad. Once you feel comfortable with finding the GCF, we then are going to factor. And factor means to write an expression as a product of 2 or more expressions, which we talked about earlier. Like, let me give a little bit better of an example, like 12. 12 we can write as 1 times 12. But that's a little vague. We prefer to write it as something nicer. Maybe we could write it as, I don't know, 2 times 2 times 3. In which this here is what we call a prime factorization. In which we broke it down into the prime numbers. This is always unique. That way we always have a correct answer. We can all agree that the prime factors are 2 times 2 times 3. Instead, when we have 12, we could be going, well, maybe we could have 4 times 3, or maybe we could have 2 times 6, which leaves a lot of room for different answers. And as you know, math isn't a fan of that. We like to have one answer that's correct. So usually we like to do prime factoring. Now, that brings up an interesting point. Let's look at 2 again. Remember, I said 2 is 1 times 2. Can you think of any other way to write it? No. But this isn't a prime factor because 1's not prime. So we always call 2 a prime number. So we could say 2 is not factorable in some sense when we get a little bit more specific on expressions. So let's get away from the numbers and let's see how we're going to factor expressions. So the first thing that we're going to factor is 3x cubed plus 6x plus 12. Now, when we look at this guy, the first thing we're going to do is identify the terms. We have 3x cubed, we have 6x, and we have 12, and they're all nicely positive for us. What we need to do is find the GCF of the terms. And it's of all the terms, so nobody gets left out. Sorry about that. So, when we look at for the GCF, we have constants and variables in the mix here. Let's go ahead and view these all separate, just like we've been doing. Let's start with the variables. They're really nice. We have x cubed, we have x, and then there's no x's. So the smallest degree of the variable is none of them. So we don't collect any x's. So there's no x GCF here. Okay. Move on to the variable part. The constant part. We have 3, we have 6, and we got 12. In fact, you can kind of cheat and look at the smallest number and see if that's the GCF already. 3 can go into itself. Can 3 go into 6? Yeah, 2 times. Can 3 go into 12? Sure thing, yeah, 3 times 4. Well, there we go. There's our GCF. And it's just 3. There's no variables. Alright, our next step after that is to factor out the GCF. So, we have our GCF in front, and now I'm going to fling some parentheses. You do have to write them, don't drop them. And go, what times 3 will get me 3x cubed? Well, the 3's already there, we have it, so we're missing the x cubed. And we go ahead and say plus. Alright, repeat, what times 3 will get us 6x? Well, 3 times 2 is 6, and we need an x. So 3 times 2x is 6x. Perfect. Alright, last but not least, plus, what times 3 will get us 12? Well, 4. And this is our factored form. Let's do one more. And let's get a little bit uglier. So let's factor. And we have 6m to the 8th plus 21m to the 6th minus 30m to the 2nd. So, what we're going to do is first find the GCF. Now, you can start with the smallest guy and say 6. Can 6 go into 21? No. Bummer. It could go into 30, but it has to go into everybody. So that didn't help us out, that cheap trick. So we'll go ahead and do our prime factorization. No harm done. We have 6 is 2 and 3. 21 is 7 and 3. And 30 is 10 and 3. And 10 can break down into 2 and 5. So there's our prime factorization. Now we can only collect what they share in common. We have a 3, a 3, and a 3. And there's nothing else they share in common, so our GCF is 3. For the constants, now don't forget we have variables. So we have m to the 8th, m to the 6th, and m squared. What's the smallest degree? M squared. So our GCF is 3m squared. Alright, so that's our first step. Next step, we're going to factor out that 3m squared, write our parentheses, and now we get to ask ourselves, what times 3m squared will get us 6m to the 8th? So 3 times 2 will get us 6. We have m squared and we need m to the 8th. So when we need to multiply same base, we add the exponents. So 2 plus what will get us 8? And that would be 6. So we have 2m to the 6. And then plus, what times 3 will get us 21? It is 7. We have m to the 6. We are multiplying what times m squared will get us m to the 6. So we need 4 more m's. And then we have a minus sign here. 3 times what will get us 30. And look, we need m squared. We already have m squared, so we don't need any m's. So this is our factored form. And that is it for part 1.